All right, welcome to the Explainer. Today, we're going to shrink way, way down right inside a computer chip to explore the seriously strange quantum rules that make our entire digital world go. Our guide for this journey is the textbook Fundamentals of Carrier Transport, and it's going to help us uncover a pretty surprising secret about how electricity really works at the nanoscale.
So, to really get what's happening inside your phone right now, we have to ask a huge question. When you're working with components this tiny, the simple rules of electricity that you and I learned in school, they don't just bend a little, they totally break. The whole game changes.
Okay, so let's start with the picture most of us probably have in our heads. It's a useful starting point, and we can call it the electron superhighway.
Yeah, in this model, it's all super straightforward, right? Electrons are just these little particles, a bunch of them flow through a wire like cars, and boom, that's electricity. Simple, predictable, easy to picture.
And, this whole idea is basically summed up by something called Ohm's law. It just says that the more you push on these electrons with voltage, the faster they go and the stronger your current gets. It makes perfect sense, kind of like stepping on the gas pedal.
But here's where things get interesting. As our technology started shrinking down to these just insane scales, engineers and physicists slammed right into a massive problem. That nice, simple story, it started to fall apart.
And you know what? This isn't even a new thing. We're talking way back in the 1950s. Folks like Ryder and Shockley were already seeing something odd in the very first semiconductors. They noticed what they called a saturation of carrier velocity, which is a fancy way of saying the electrons just weren't cooperating with the old rules.
So here's the whole problem in a nutshell. On the left, you've got the theory, Ohm's law, which says speed should just keep going up and up with more voltage. But on the right, that's reality. That's what's actually happening inside a modern chip. You push harder and harder, but the electrons, they hit a speed limit. Their speed, their velocity, just flatlines.
This is the multi-billion-dollar question. For real, why? Why is there this microscopic traffic jam happening inside our most advanced gadgets? What in the world is causing this invisible speed limit?
To figure this out, we have to throw that whole billiard ball idea right out the window. We need to leave that simple world behind and step into the totally weird but fascinating world of quantum mechanics. The key to this whole mystery is actually right here in this diagram. It shows us that to really get what's going on, you can't just think about the electron in one simple way. You kind of have to hold three completely different, almost contradictory ideas in your head all at once. Okay, first things first, forget the tiny ball. At this scale, an electron behaves like a quantum wave. Seriously? Picture it spreading out through the atomic crystal structure of the material, kind of like ripples moving across a pond.
But, and this is where it gets really strange, at the very same time, it also acts like a particle. Not one that's flying straight, though. It's constantly getting knocked around, scattering off these tiny vibrations and imperfections in the material. Think less like a car on a highway and more like a pinball machine. So you've got this wave, you've got this scattering particle. What does that even mean? Well, our third viewpoint sort of combines the two. Because it's both things at once, you can never actually know exactly where the electron is. It's a bit spooky. All you have is this cloud of probability, just a mathematical description of where it's most likely to be. Okay, so we've got this weird wave-particle probability thing. But its behavior isn't just about what it is, it's also about the journey it's taking. And that journey is through a kind of quantum obstacle course. Check this out. On the left, that's what an electron wave looks like in empty space. It's nice and simple, regular, predictable. But on the right, that's the world inside a silicon chip. It is a chaotic, bumpy, super complex landscape of electrical forces created by all the atoms in the crystal. It is anything but a smooth ride.
Yeah, this landscape, physicists call it a periodic potential, is that quantum obstacle course I mentioned. The electron wave has to somehow navigate this incredibly complex terrain. And just by doing that, its own properties and the way it moves are completely changed.
And here it is, the big reveal. That speed limit, that velocity saturation, it's not a bug, it's a feature. It is the totally natural, unavoidable result of that electron wave interacting with the atomic obstacle course of the chip. The material itself is the traffic cop.
Okay, so why should we care about all this mind-bending theory?
Well, because if you're an engineer designing the next generation of computer chips, this isn't just theory. This is the rule book. This is the instruction manual for building the future.
And that brings us to what carrier transport really means. It's not about simple flowing billiard balls. No, it's the super complex science of how these quantum wave particles navigate the atomic world inside a material, all governed by the strange new rules we've just been talking about.
All right, let's do a quick recap. First, forget the billiard balls. That model is broken at this scale. Second, you got to think of electrons as being both waves and particles. It's weird, but it's true. Third, the material itself. Its very atomic structure sets the speed limit. And finally, engineers have to master these quantum rules to keep making our technology better, faster, and smaller.
And all of this leaves us with one last big thought. We've peeled back one layer of quantum weirdness to understand today's tech, but as we keep pushing the limits, building devices that are only a handful of atoms wide, the question is, what even stranger quantum rules are we about to discover next?